Hi, yeah, I'm Dr. Rupert Perkins from the School of Earth and Ocean Sciences at Cardiff University. So the project title is Natural Coastal Management. So what we're really interested in is how coastal erosion can be manipulated through natural processes. And at the moment this is a very important subject area because with sea level rise we're getting increased coastal erosion, and also with more land reclamation in the coast we've got this double whammy of coastal squeeze. So the land is basically being reclaimed inland and it's being eroded by the sea and the increasing sea level. So coastal management is incredibly important to try and stop that process getting worse. So we are trying to replace the traditional mechanisms of big concrete seawalls which cost £1,000 a metre with going back to nature and working with nature to try and do something about the problem. So we've been going out into the field, into estuaries, and measuring the resistance of the mudflat to coastal erosion and how that can really be enhanced so that we can try and have what the process called managed realignment, where you revert back to the coastal defence mechanisms of salt marshes and mudflats instead of these expensive seawalls. So we've been going out and we've been measuring the strength of the mudflat, and you do that with what's basically an expensive water pistol called a cohesive strength meter, as far as a water jet into the mud. And what we've seen is where we've got microalgae, single-celled organisms which produce sticky polymers that bind the sediment together, we've seen that you can increase the resistance to erosion by a factor of between 5 and 10. So these biological polymers that get produced play a real ecosystem service, a real financially valuable service to us, in that they stabilise the mud, and that then leads to plants colonising, salt marsh plants, and then you gradually get more and more mud building up to produce your own sea defence, which is the salt marsh. So we can go to areas which are suitable and start to manipulate this to really sort of allow this natural succession into this natural buffering system to stop coastal erosion. Okay, so the conclusions are that it's better to work with nature than against it, and it's effectively an ideal scenario where you've got biological processes that we can measure and then we can manipulate, and then we can decide whether it's suitable to actually have this managed realignment. From the point of view of a case study, it then gives you the opportunity to see how coastal geomorphology, geography, and coastal management, human geography, and biological processes are all interacting. So one thing you can do in the classroom is a whole series of experiments where you can actually visualize this strengthening of the coastal sediments and look at how biological polymers can do this. So what I've got here, typical Blue Peter style, is one I prepared earlier. So what we've got here is mud and water, and you don't have to be a genius to see that that's not actually going to resist any kind of erosion. It's just sloppy, muddy water. And if you didn't have biological polymers in here, mudflats would be not far off this. Mudflats typically about 50% of water content. So as soon as the tide comes in, they get eroded. What we've got in here is biological polymer. It's something called blanos, which you can buy very cheaply from a chemistry stores. So it's really quite easy to get hold of. And as you can see, it's sticky goo. And this is the polymer that bacteria and algae on a mudflat are producing, which sticks the sediment together. So effectively, you can start with this, and it's got no solidity, no strength to it at all. And then you can start to add this to it. And stir in your biological polymer. And as you stir in the biological polymer, you see, try not to drip on the floor, it starts to get a little bit thicker. And you can do experiments where you just add more and more polymer, and then you can leave it. And the important thing is that as you add the polymer, you give it a time to dry out. And that drying out is low tide. So tide goes out and this polymer then starts to bind with the sediment. But you can see already, it's already starting to bind that sediment together. And then what you can do, if you're sitting somewhere and it's not your carpet, so you don't worry about it, is you can start to pour this onto slopes. You can measure the slope, the speed that flows down, and you can do a whole series of experiments looking at how biological polymer changes the viscosity of the sediment. Or you can do some slightly messier versions where you have a whole series of pots like this with the mud and the polymer together, and you can drop marbles into it and you can see what depth the marble goes to it, and then you can actually dry it out simulating a low tide, and you can see just how far that marble sinks. So there's a whole range of nice messy experiments that students can develop and work out for themselves, playing with simply just mud, water and this polymer, and it's a really nice visual way of looking at how the biology stabilises sediment and protects our coasts.